Okay, hello everybody. This is the second lecture of the week. And as you remember that we just started the topics for hydrology. And today I'm going to talk about rainwater and stormwater. And I'm going to introduce you two important topics. It will be great if you turn on your camera. I like to see you. And please ask me any questions if you need any answer. Or if you want me to repeat anything, just do it timely while I'm speaking. Don't worry, just ask directly and I will repeat or answer the question. And again, I'm repeating you. Could you please turn on your camera? Yes, great. It's good to see you. Okay, guys, let's start. Okay, I'm going to start. As you remember that I was talking about rain and rain data. And I like to start with you this particular example. Actually, I designed this presentation slide as a kind of question, but I am going to use it to explain you the topic, okay? So think in that way, guys. You are civil engineers, okay? Your main responsibility is to design civil structure, infrastructure. And also Kazakhstan is a kind of country having frequently or very often some flooding events, okay? So these are like disasters. So the main problem is that, of course, the geological structure is important, and maybe some cities are constructed or located on over the flood basins, but still, if a city, okay, or if a district is impacted by flood, it is a kind of mistake of engineers. Engineers should design it better way and estimate any risk, including heavy amount of rains, okay? So that's why this topic is particularly important for Kazakh engineers. I want you to ask, please listen carefully and try to understand it. And here there's a graph, and this graph is a probability graph. Graph will help you to understand and estimate how likely an event can return back, okay? It is called return period, okay? So you are going to design a project by considering the risk of returning of an event or a catastrophic event back. So it means that, think about, you have a district, and this district has some extreme rain events during the last 50 years. And those rain events has created lots of flooding problems, and city is suffering from this problem. And the first thing is that while you are making a kind of design of an infrastructure, you should analyze the likelihood or probability of the rain event, how often it can return back, okay? Then you will make a kind of design accordingly. And in this case, we are going to use this equation. It is probability equation. It is given on the screen. Please have a look at that. And the graph on the right side is just the same expression of this equation. So you can use either this graph or this equation to solve a problem in this regard. So you can follow both of the methodologies, using graph method or using a kind of probability equation. I am going to solve one problem after this. So for example, let's have a look at that. What this graph is telling us. The first thing is that, what is this I? Y means the next years you are focusing on to make a project or estimation. For example, if you are trying to make a kind of project design for the next 5 years to make a kind of risk management for rain in an urban district, okay? So it is going to be your point. I mean, number is going to be your number here is 5. And there is another unknown here. It is N. N is return period, okay? Return period of an event. So by using this chart, you can estimate that how likely, like 90%, 50%, 65%, 95%. These are the probabilities of the return period of that event in a given time. Okay, so let me solve one problem, then you will understand in a better way. Okay, so let's have a look at the question given on the screen. And assume that there is a storm having a 50-year return period, okay? So You are analyzing the data as you remember that I gave you data like this one. Have a look at that. There's a storm here. Okay, there's another storm here. These are also storms. You can assume that any event over 800, for example, is a storm. So you can easily estimate that how likely a storm is hitting Almaty. Okay, so you may see that typically every 10 years a storm is coming back and hitting the city, and it was even often during this period. But before 50s, I mean 1950, there was not a kind of, not that frequently. But after 1950, something happened, and the city has started experiencing more flooding events or more heavy rains. Okay, so you can use such a data to make an estimation for this parameter. Then the question is that if your design period is 5 years, so you are designing a kind of, for example, parking area or a kind of street, you are making a kind of design for any infrastructure, and your design period is 5 years. So I want you to make a kind of estimation that how likely that event can come back and hit the city in 5 years if it is coming every year, in every years, okay? If it's coming in every year. I mean, it means that you experience this problem in every years, very, I mean, with high probability. It hits the city at least one time in every year, every 50 years. But what is the likelihood of having that event in the coming 5 years? Okay, this is what we are going to estimate. And then it's quite simple. You are going to find 5 years, and you will go up with 90% probability, and then, sorry, you will check it out with 50 years, and then you will see that it is 90%. So it is very likely that you are going to have such an event, 90%, with 90% likelihood in the 5 years period of time. So you can use the same equation as I introduced you here. You can write here 5, and 90% is the expected probability. So then you can estimate that in 90% probability, you will expect this event in 50 years period of time. Okay, so the equation works in both ways. The equation works in both ways, and if you increase the probability or if you decrease the probability, then you are going to have different numbers. It's about what do you understand as a risk. Okay, so some cities are considering that some risks over 90% is a kind of risk you can tolerate, but some city managements are saying that it is not a kind of risk we can accept. Maybe they are reducing it into another level, like 80%, 70%, but these are all about engineering. But in this part of the lecture, I'd like to introduce you that how you can use probability to make an estimation of likelihood of returning period of any extreme event for an expected design period of a project. Okay, any questions, please? It might look like a little bit confusing, but it is, I mean, as an engineer, if you think that it's quite straightforward, just what you need to know that what this figure is telling and what is a return period and what is the expected project time, I mean, the projection time you are focusing on. Okay, so that's why I use different colors here to differentiate you how you are going to make the calculation and expectations, I mean, the probabilities. And again, as I told that most of the time we are going to focus on 90% probability. It is risk threshold, and if anything is lower than 90%, it is risky. If it is more than more than 90%, it's risky. So it also works in the opposite way for any parameter, any values less than 90%. Okay, guys. And another thing you should learn, actually, you might remember that I was talking about IDF graphs. Here, I told you that in the earlier week, this is an IDF graph, but I couldn't find a graph for Astana or Kazakhstan or Almaty, any city in Kazakhstan. So that's why I'm going to use some other data from other cities. And this is another IDF graph, okay, which is telling us how the rain is hitting the city. And at this moment, I like to explain you that there is one concept. It is called the areal reduction factor. Okay, let's think in that way. While we are measuring the rain, there is a kind of cup like this one. Okay, these are actually called meteorological rain collectors. Okay, so in every meteorology station, they are using a cup located on the ground, and when it starts raining, they are just collecting rain in that cup, and after the rain, they are measuring it. Okay, I mean, they are measuring how much rain is collected. But the thing is that you are collecting the rain in just one location. But if you are talking about the amount of rain you will collect over an area, it's totally different. Okay, so that's why you have to apply an area reduction factor to estimate the amount of rain you will collect. And why we need such a kind of calculation factor? Think in that way. For example, you are working for Nur Sultan municipality and you are a civil engineer there, and you are going to make a kind of design for water collection systems for rains. Okay, so rain collection system, it's a huge investment project. And if you are making a kind of rain collection system design, okay, a kind of infrastructure project, the first thing is that you should know is the amount of rain. Okay, the amount of total rain you can collect in the given area, or Nur Sultan area, for example, or over a district. Okay, so as I told you that the meteorology stations are going to provide you data only for one single location, but the area is a different concept. Okay, in order to calculate the amount in an area, you can use these IDF graphs. Okay, so I'm going to show you that how to use. Even I will solve you one problem. The first thing is you should understand that there are different IRF factors, area reduction factor for different structures. Okay, for example, if it is a meadow area, the IRF function is going to be different. If it is an urban area, it is also going to be different from urban to, I mean, place to place. It's about the urbanization. It's about the structure. Everything is there. So the first thing is you should know that what is the size of area you are making the design. Okay, you will find it. And then you will also make design for selecting proper rain type. Okay, so for example, if you are making a kind of design for typically 30 minutes rains, so the duration of rain is also very important. I remember that when I was making my PhD, I was working on rain data to make some infrastructure design, and I was making a discussion with a professor, and I said that, okay, typically the rain events in that city, what I was making design, is like 30 minutes. And that professor told me that, are you sure that? He said, is it possible to have a 30-minute rain event? I said, yes, typically it's 30 minutes. And he said that, no, there is no way. A rain event cannot end, I mean, in 30 minutes. I don't know what is your experience. Typically, how long it takes for a rain event to continue in Kazakhstan. I mean, I've been living here for 5 years, and in spring period, the rain events are typically around 1 hour. Okay, it doesn't, I mean, they don't last for a day. But for that professor, he was living in a different climate zone, and the rain events are minimum 12 hours or 24 hours. And think about monsoon season, for example, in India. Okay, so when it starts raining, it rains for even a week. So what I'm saying that every city, every region might have different different amount duration of the rains. That's why there are different graphs here. Okay, so let's assume that you are going to make the design for 30 minutes of rain, and your area is 30 kilometers. Go up, hit it, and go back, go left, and you are going to see that your area reduction factor will be something between 0.6 and 0.7. It means that while you are calculating the overall amount of water you can collect over that area, you should use this reduction factor. Okay, let me solve you a problem and you will understand in a better way. Let's have a look at what we have here in this problem. Okay, the problem is saying that it's on the screen now. What is the average 2-year 1 hour rainfall on an area of 50 kilometers? Okay, if the point value is 40 millimeter for an urban catchment. Point value means that the amount of rain collected one point is 40 millimeters. then you are going to convert this point value into area value. Okay, so let's see that this is the chart you are going to use, because it is 1 hour rain event data. Okay, please follow on the screen. And this is the area, 50 kilometers, and I'm going to hit this. Then I will go left, and you see that this is the score I'm going to read. It is around 0.65. And when I perform the calculation, it's going to happen in that way. So the rainfall will be corrected by multiplying this to 40 millimeters. Then you are going to have 26 millimeters rain, actual rain over the area. And if you multiply this value with the area, then you are going to have 1.3 million cubic meter water you can collect in that catchment area during that rain event. Okay, so whatever you design, a kind of sewage system, rain collection system, treatment system, whatever it is, you should use this amount of volume to make your design. Okay, and you should collect this amount of water during 1 hour. This is also critical later, I mean, while you are making a design for rainwater collection systems. Okay, any question about area reduction factor, guys? This is the second topic you are going to learn today. No questions? Is everything clear? Wow, surprising. Okay, no questions. Okay, let's continue. Okay, do you know what is the runoff water? Anybody knows that what is runoff water? Have you ever seen runoff water in your life? Guys, this is runoff water. Look at the screen. And during rain or after the rain, if there is a water flowing on streets, for example, it is runoff water. Okay, so this type of water during the rain event or after the rain event, those street lines are called runoff water. Okay. And runoff water in streets, they will go to strong drains along streets, and they will be collected, and they should be, I mean, removed from the city. They should be conveyed over the city to protect city. And please note that rainwater can be considered as clean water. Okay, and if you treat it, you can even use it as a kind of drinking water or agricultural purposes. So it is fresh water. We don't want to dump it. That's why most of the cities, if they are suffering from freshwater resources, if there's a scarcity in terms of fresh water, so they collect it and they use this water. It is precious. It is important. So you don't want to waste it. You don't want to pollute it. That's why in many European cities, they have separate rainwater collection systems. It's separated than sewage system. But in Astana, my experience is limited with Astana. I didn't check the other cities in Kazakhstan, but in Astana, rainwater and sewage systems are combined. So I don't know. Most probably, the rainwater is going the same way as sewage goes. Okay. So it is important for urban management, and you are civil engineers, as I told you. You are going to be civil engineers, and guys, you are going to design. Okay, you are going to design sound and good streets, sound and good urban structures. Okay, please have a look at this picture. It is a very nice picture. I like it. This is a typical design. This is wrong. Okay. Sorry, this is right. Water goes onto the streets and collected in a sound way. They are using also some permeable grounds to collect water. Okay, but here there is a wrong design. It flows over the ground. It flows over the streets. It is still collected, but you can see that there are lots of puddles over the streets. So it is a kind of indication that it is a bad design. Even if you walk around the campus, Nazarbayev University campus, especially nowadays, because it's melting time, snow melting time, you will see that there are lots of water puddles everywhere. It means that our infrastructure design is not also good. Okay. So typically, while we are designing a kind of urban runoff infrastructure design, we construct catchment basins, which collects the water which is drained from the streets. And then also there could be some discharge pipes and associated structures to collect, convey, and transfer it. And also there should be other structures to prevent water from flowing over the ground, okay, like flood basin control for the streets and buildings. And also you can install some filtering systems through the soil before ending up in surface or groundwater. This is also very good applications. Even in the developed countries like in the UK and other countries, I saw that they are now using or constructing some permeable asphalt for roads. It's called permeable pavements. They are constructing it. It means that when rain falls on it, okay, precipitation falls on it, it directly goes in the, I mean, it filtrated over the asphalt. It doesn't create any runoff. These are new designs. I have never seen such a design in Kazakhstan, but in some developed countries, they are making such designs. There are such materials also available. And if you are interested in, please make some readings and do some search on YouTube. You will find very interesting video, which is showing that even asphalt, even pavements are like sponge. They are just absorbing the water instantaneously when it falls on it. And while we are estimating the amount of runoff, there are lots of factors. Some of factors are related to meteorological parameters, but some of the factors are related to physical characteristics of the topography and the water basin, or let's say catchment area you are studying. Okay, for example, type of precipitation is important, like rain, snow, and streets. Rainfall intensity, rainfall amount, and rainfall ranges are the most critical parameters among the other ones. And in terms of physical characteristics of the catchment area, the most critical one is land use, vegetation, and soil type, and also slope is important. Okay, so while we are making a design for streets in urban area, I think the slope is the most critical parameters. And in terms of meteorology, the most important parameter is what is the characteristics of the rainfall. And have a look at here. Okay, now these are two additional topics before starting interception and depression storages. I'd like to stop here and ask you if you have any questions, guys.
Sir, may I ask?
Yes, please, Aidana.
I wanted to ask about the runoff waters.
Yes.
Like, does the storage of runoff water differ in different countries?
Yes, I mean, runoff water is very important in some countries. For example, if you are living in Singapore, do you remember that in earlier course I told that they are drinking tea, but instead of tea, if they have rain, they like to drink it. Okay, so that's why they are just storing that runoff water in a basin, mostly because the amounts are huge. Well, look at that in our earlier calculations. This is a huge amount of water. I mean, you cannot easily construct a structure, but in those instead of structure, they are just collecting that amount of water in a like an artificial lake. Okay, and later they are using it by making some treatment. They are using it for drinking as a drinking water or other. So typically, this is what they do. If they have problems in terms of water scarcity, like water scarcity, but some countries are just discharging it. For example, I spent lots of time in Istanbul, and in Istanbul, no one use rainwater, but it is collected, but discharged directly into the sea. Okay, so rainwater goes into the sea, but this is not a good management because now city is suffering from freshwater resources. There is not enough fresh water to sustain 20 million people. That's why now, for example, in Istanbul, they are talking about to have another infrastructure, okay, like a kind of separate infrastructure only for rainwater collection. And they are trying to get some good quality water from rain to use as a drinking purpose. But these are huge investments. I mean, they require billions of dollars to make such a kind of investment in such large cities. So that's why guys, these analyses are important, I mean, in civil engineering. So my answer to your question is that yes, some cities, some towns are making a good management to keep it. Some cities are not managing them in a good way, just discharging it. And also it's interesting, Aidana, it's about what you have and what you have to use, okay? For example, there is a city in Finland, its name is Turku, okay? I don't know, if you have a chance, go there, it's a very nice city. And when I was there, actually I was teaching in Turku University for a short time. I worked at university as a visiting professor in Finland, Turku. So the city was quite interesting, but it is like Astana. I mean, when it starts raining, I mean, I'm talking about snow, it was staying on the city almost 8% of the year. It's a cold city, and most of the time, the snow, I mean, the precipitation is in this form of snow, okay? And I don't know, are you familiar with the people who lives in Finland and in that region? They like cold weather, okay? Like some Kazakh people. For example, my neighbor, he's a Kazakh man. He's always opening the window while he's sleeping, even in the, just middle of the winter. Because he likes cold weather. Maybe some of you are the same, but I am not. I don't like cold weather. Okay, those people like cold weather. And also I mean, when the time comes to summer, they are complaining about the heat. Actually, it is not that warm. I mean, Turkey is always a kind of cool or cold climate, but even those people don't like very like 20 degree, okay, 25 degree outside. So they are using AC systems in the cities, and Turku city found a very interesting solution. Do you know what they did? There is a large mountain over there. They just dug out the mountain and they constructed a water treatment plant in the mountain because they need a kind of space which is not freezing during the winter, and it was a perfect place. And also, while they are digging it out, they just made another large reservoir in the mountain, and in the winter they are just collecting water from citrates, not water, the snow from the citrates, as we do. For example, in this campus, I observed that in every single morning, there are trucks collecting snow, okay? I don't know where that snow is ending up, but in Turku, they are just filling that mountain in the snow, with the snow, and it turns into ice, large ice cap in the snow. And when the time comes to melting, they are using that water as a kind of cooling water and replacing that water with heating water. I mean, the heating system is the same like Astana. There is a kind of district heating, but in winter, in summer, they are pumping hot water to heat up, but in the winter, they are pumping that cold water, melting from the snow, to the city. And if you go to Turkey, you will see that all the radiators during the summer period, they are cold. And cold water is just coming from that mountain, which was stored during the winter period. So this is a quite a good example to explain your case. So every city has their own characteristics, okay? So rain is important because it's clean water, and every city should find a way to use it for the best way based on their needs. Did you get it? Okay, I don't know if the question is good enough to satisfy your I mean, as a kind of satisfying answer. I don't know, but this is the answer. It's a little bit long answer anyway. Okay, any questions more, please? No? Okay. Now it's time to learn what is interception and depressive storage. Okay, these are two new terminologies maybe for you, but in hydrology they are well-known terminology. Okay, I am going to explain you simply what they are. Okay, interception means that when it starts raining, a certain amount of rain will stay on plants. Okay, think about that. You have a grass cover on the ground, okay, and first those grass cover will get wet, and that grass will keep a certain amount of water over its body, okay, their body. So this is called interception storage. And based on the amount of rain, the interception losses, the interception storage, the amount of water intercepted by the plants is considered as a loss because they don't penetrate into the surface. They don't create any runoff. They don't penetrate. They don't infiltrate into the ground, and they will just stay on the plants, and they will be intercepted by plants. And the thing is that you should be able to estimate that what is the amount of percent. Okay, so here it is a graph showing us that, for example, if the rainfall is around, for example, 10 millimeters, you see that almost 50% of the rain is just lost because of the interception. And there are different interception values for different, sorry, different type of surface covers. And considering that most of the Kazakhstan covered by meadows, you may assume that typically its interception value for Kazakhstan is around 2 millimeters. Okay. Even it may go up to 4 millimeters if there is a kind of cropland. And depression storage is another terminology. You should know it. Depression storage is this. Okay. Do you see that? This pretty woman is trying to walk with her baby over a pond. I mean, water pond, which is on streets. And if you go and walk around the campus, I think you will see that everywhere is like this one. It is not good engineering actually. So this is called depression storage. So a certain amount of water will stay on ground. Okay, but by time it will also infiltrate in the ground. Okay, it will infiltrate in the ground, but you will assume that a certain amount of water will stay on the ground as a depression. Okay, and the depression volume will be calculated by using this equation. And in this equation, there are two parameters you should know that. The first one is ST, which is the total storage capacity of the ground. The second one is PE, it is the rainfall excess. So if it is asked, I mean, if I give you a problem and if I ask you to calculate the volume, okay, the volume of the amount of volume stored, okay, then you are going to use this equation, and you should consider into account that the amount of depression to make an estimation for the rain. So simply, let's say in that way, you have meteorology data. Okay, meteorology data is collected on one point. In order to convert that meteorology data into area, you are going to use EF, okay, IFR value, area reduction factor you will use, and you will convert that value into area. Then you are going to calculate. You are going to calculate the total available water falling on the area. After that one, you are going to reduce a percent of that value for interception, okay, by using such a chart. If it is around 50 millimeters, for example, let's go and check this question again. Again, it's 40 millimeters, okay, the amount of rain. Let's go and check. If it is 40 millimeters, then interception is around 25%. Then you are going to remove 25% of this value for interception, okay? Then the total available water can be calculated by using this equation, okay? By, if of course ST and PA values should be provided for you, then you can calculate the total available water volume, okay, for at that certain time, and then you are going to make a design. So if you design your infrastructure by using only this 40 millimeter data, you are going to end up with a wrong design. Okay, you have to follow this sequence. You first calculate the IRF factor and calculate the total amount for the area you are studying for. Then you should calculate, you should also estimate the interception loss, and you should reduce that amount from the total amount. And then next, you should calculate the depression storage amount, and also you should estimate that amount should be also reduced, and you will calculate the total amount of volume. Okay. Actually, here the ST value is, we may consider that ST value is the amount of water after reduction of interception. Okay, and this is the details about how you can calculate the runoff by using rain data, runoff water by using rain data. I don't know. Hi, okay. I asked a question. I see your chat in message right now. Okay, guys, this is the end of my lecture for today. In theory, I think I explained everything and how you are going to follow the methodology to estimate the correct amount of volume. Okay, I don't know. Maybe I can solve you one problem to explain it in a better way, but I think everything is clear. So I will continue next week for the hydrology topics. Okay, do you have any questions at this stage?
Yes, Professor.
Yes, please.
Regarding the volume calculation, why the evaporation is not considered?
Yes, it will be considered. I am going to edit it on next week. Don't worry. Evaporation. But Takmina, the thing is that, okay, let me explain. This is, guys, this is a very good question. But evaporation is mostly considered, okay? So this interception is also, okay, this interception is also means evaporation, okay? So because a certain, like 20% of the water intercepted by the plants, and it is going to evaporate inevitably, okay? It will not go into the infiltration process. But as we are civil engineers, while we are making designs, evaporation is more critical for reservoirs, okay? I mean, the water reservoirs, not during the rain. Rain is a kind of event. It's mostly occurring in a couple of minutes or like up to an hour. Okay, let's say that it's happening in 1 hour. And during this event, we are just ignoring the evaporation because it is very, very little. Even it might be not possible because think about that. It's raining. And do you think that it's really possible to have evaporation at the same time? So what we are now discussing that, how we can estimate the runoff water by using rainfall data. Evaporation is important for reservoirs, okay? So we are going to consider it in the next part, okay, while we are talking about reservoirs. But now we are focusing on runoff water. In runoff water, there are three critical things. The first one is that how you will calculate the area, okay? I mean, the amount of rain for an area, because we are making the measurements on only one point. And the second thing is that you should also estimate the interception. And interception is also evaporation, because think in that way, the water is going to stay on the on the grass, okay? And maybe you can also observe that after the rain, go outside and you are going to see that all the grasses are wet, okay? Because they intercepted a certain amount of water. As there is a certain amount of water on the grasses, but after 2 hours, it is going to disappear. It will evaporate. So what we think that, I mean, in theory, that interception is also includes the evaporation, the losses by evaporation, because inevitably that amount will evaporate and we are going to lose it. It's clear. Did you get it? Did you get the trick? Okay, for rain, there is no evaporation, but evaporation is included in the interception amount, okay, by the plants. Any other questions, please? Okay, I think
for rain there is no evaporation, but what about tropical regions? It's really hot there, and the tropical rains.
Yeah, maybe after the rain. Again, I am repeating you that. If we are talking about soil wetness, if we are talking about underground water levels, if we are talking about reservoirs, okay, evaporation is critical, okay? Especially for reservoir management, evaporation is one of the most critical parameters, okay? For example, in some hot climates in the US, like California, they are just using some black balls, okay, to cover over the reservoirs. I mean, you have seen some video maybe, most probably, and to minimize the amount of evaporation escapes for the reservoirs, okay? Yes, you are right. For hot climate places, evaporation is important, but not during the rain, not for runoff, okay? It is coming into account after the rain. It is something else you should consider for reservoir management, for soil management. But we are civil engineers, we are not really interested in soil management. It is not our scope. As we are civil engineers, we are interested in runoff water because it's important to make a kind of drainage system design, okay? Guys, you are going to make the drainage. I mean, the design of drainage for any building. Okay, you may think that, okay, as a civil engineer, you are going to design only structure. No, you are also going to make a kind of drainage system design. And in order to make such a calculation, you have to analyze rainwater, and you have to analyze the amount of runoff water you have to manage, okay? These are essential information for civil engineers. And the second important part of civil engineering in hydrology is reservoir management, which is something else we are going to discuss it later. Okay.
Okay, thank you.
Any more questions, please? No? Oh, okay. It's good. It's not good. If you ask me questions, it's much better, but it means that time is up and okay, it is Thursday and the lecture is over. Yeah, it's good anyway. Okay. Thank you very much, guys, for your patience. And if you do not understand any topic while you are studying, please also text me, send me an email or another stuff. And please also note that I am working office now. Okay. So it will be possible that to ask me any personal questions, I mean, or in-person questions, just stop by my office anytime in the daytime, and I will be happy to make you any explanations or discuss the topics if you need. So noting that I am mostly working office now, not home-based work, so you can find me easily in my office if you need to discuss or ask any questions. Okay, bye-bye. See you next time.
Bye.
Thank you. Goodbye.
Bye. Thank you.